Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
Oh, hey, that's me. Hi, I'm Dr. Moiya McTier. I'm an astrophysicist and a folklorist and friend to the universe. I know because I have its phone number memorized. It's 0.
I'm like, it's 555 1 2 3 4. I'm Corinne Caputo, writer, friend to the universe. I don't have the universe's number, but that I might.
Well,
it's
now
just
you
not
do.
Saved. Now I know it. I do have numbers in my phone that I've never assigned a contact to, and then they like send me a very friendly text, and I'm like, who was that?
Who is this stranger? Yeah, you know, you have to reach a threshold of familiarity for me to actually put your name next to your number in my phone.
I'm realizing the newer friends I make, like as an adult, I don't know their last name always right away. Like, I think it was kind of different when you're younger, or like you're in school together where like last name is like way more a part of the culture than
part of the culture. Yeah. No, I definitely just put people's last names as however I know them. So they'll be like, Tiana, Corinne's friend or something.
Yeah. Yes, exactly.
Where are we today, Corinne? This is gorgeous.
I love it here. This is one of my favorite spots. This is the Brooklyn Botanic Garden. The cherry blossoms are here. And it's spring, so this is probably the last week to really see them before it just becomes, lush green, which I'm very excited about. But it is funny how short-lived the flower experience is in spring.
That's true.
So it's good we came.
I agree. Yeah, I'm glad we're here this week. It smells so good, and, I know it's the last week because all of the petals are falling down on us, which is a very picturesque scene.
Yes. A little bittersweet, too. I remember being a kid and being sad that the petals were going.
Yeah.
But
it's a cycle of life. That's what happens. Speaking of the cycle of life, today we're going to be talking about the end stages of a particular type of star. So I think that, these types of stars are like the fallen petals.
I love that. The Beauty and the Beast, kind of. The rose.
Yeah, I'm trying to make the connection work, y'all. So we are talking today about neutron stars. Corinne, do you have any thoughts or questions or concerns about neutron stars before we get started?
Okay, my concerns. Let's see. I don't have many. Neutron to me was a word that I swear to God I first heard through Jimmy Neutron.
Yeah.
So I often associate that word with a strange computer animation of a little boy with crazy hair.
His hair is weird looking. I remember there was an episode, or maybe it was in the movie, where he created a machine to do his getting ready routine in the morning, and it like brushes his teeth and does his hair in that wild do.
I can picture that machine. I know exactly what you're talking about. It is it's impressive hair.
Yeah. I think we also have nice hair.
I think we do
Corinne.
too. My hair, I'm definitely getting used to this cut, but we're making it work.
It takes time. You'll get there. Okay, so no real existential concerns about neutron stars. No preconceived notions about them.
No.
What do you think a neutron star is, Corinne?
Okay, so it's a end of life stage of a star.
Yes.
It's not like a specific kind of star. It's like a stage of a star.
Yes.
Okay, love that.
Yes.
That's kind of all I know.
Okay. That's great. Then let's get into it, and hopefully by the end of the episode you will have added to your neutron star knowledge. So you were totally right that a neutron star is like a stage. It's the last stage of a particular type of star. And we have a stellar types episode, so if you haven't listened to that, go listen to it and pay extra close attention to the high mass stars, because that is the type of star that creates a neutron star. So neutron stars are what gets left over when a star that's about 8 to maybe 30 times the mass of our sun ends its like life on the main sequence and stops fusing hydrogen into helium in its core. So that mass range, 8 to about 20 or 30 solar masses, that does depend on the metallicity of the star. And I know we've talked about metallicity before. So if there are more heavy elements in the star, then a lighter star, a less massive star, can turn into a neutron star. So there is that metallicity dependence, which I think is really cool. So when one of those massive stars stops fusing all of the hydrogen in its core, it's going to blow up in a supernova explosion, particularly a type 2 supernova explosion. And there are different types of supernovae. I'm sure we'll do an episode on that in the future. But then it explodes, but there is this core left behind, a very, very dense core. If the star were any more massive, it would turn into a black hole. We also did an episode about that, so go check out episode 16 about black holes. But still, neutron stars are the second densest types of objects in the entire universe that we have discovered so far. Yeah, they're really cool. It's an extreme environment, and so weird physics happens in neutron stars. The type of physics that we don't totally understand yet, because we can't go to a neutron star and cut into it and see what's happening. So this is theoretical, this is based on simulations, this is based on observations of as many neutron stars as we can find, but there's still so much more to learn about this particular type of star, and that just makes me really happy.
Yeah, they sound really fun.
They are very interesting. Do I know any neutron star astronomers? I do know neutron star astronomers, but none of them that are weird enough to talk about. I know some astronomers who have bright blue hair or entire back tattoos, and those are really cool people on paper. I don't know any neutron star astronomers like that.
If you're a very cool neutron star astronomer, please send a picture in.
Please reach out. Let us know what makes you cool.
And we'll describe you on the pod.
Although I do think that studying astronomy in general can be enough to make a person cool.
Oh, absolutely.
It is sufficient, but not necessary. So let's talk about the density of these neutron stars a little bit. They are so dense that electrons in the atoms that make up this star get smushed into the nucleus of that atom and combine with the protons in the nucleus to make neutrons, which is why it's called a neutron star. About 95% of the body of the star, we're pretty sure, is made of neutrons. But not just naturally occurring neutrons in the nuclei of these atoms, but neutrons that were created through a process called electron capture, where the electron gets smushed into the nucleus, and I think that's very cool. So this isn't a main sequence type star. It actually does kind of bother me a little bit that we call it a neutron star at all, because the definition of a star is a massive ball of gas that is so hot that it fuses in its core. But neutron stars aren't fusing anymore. So they are not generating new energy and heat through fusion. They are just radiating away the heat that they had in them after the supernova explosion. So they're not really stars, but we call them neutron stars anyway. Whatever. Astronomers aren't the best at naming things. That's just going to be a constant throughout this podcast. But at the beginning, when a neutron star first forms, the surface of the neutron star can be about 1,000,000 degrees Fahrenheit.
Hot.
They are very hot. And then it cools down over time. The neutron star is also going to be spinning, because everything in space is spinning, and a neutron star would have formed from a main sequence star that was also spinning, and it maintains that angular momentum, but over time it will start to spin more slowly. And so it cools down and it spins down over time. When we're talking about the size of a neutron star, they are very small. They're the size of a town, they're 10 to 25 miles across.
Oh my God.
So small. But their mass, they have more mass than our sun. The typical mass of a neutron star is 1.4 to 2 solar masses. So it's a very narrow range.
How does that even work?
Heavy.
How can something be so dense and so small?
Exactly, Corinne. It is extremely dense. Dense enough to smush the electrons.
Yeah.
Neutron stars should be about 0.1% of stars. They should account for 1 in 1,000 stars, because we know what types of stars these form from. These are going to form from like A and B type stars that are just slightly more massive than our sun, but not massive enough to form a black hole. And we know how common those stars are, so we can just take that fraction and turn it into the fraction that we expect for neutron stars. And if we keep that fraction of 0.1%, then that means there should be about 100 million neutron stars in the Milky Way galaxy.
Whoa, they're everywhere.
Big numbers. They're everywhere. And we have found a few thousand of them. Let's dig into the history a little bit. The concept of a neutron star was first predicted in 1934 by multiple scientists around the same time. So in the Soviet Union, a scientist named Lev Landau hypothesized the existence of neutron stars. And then over in, I guess, maybe Switzerland, or over in Europe, it was hypothesized by Walter Baade. Great name.
Baade.
And Fritz Zwicky, another great name.
Those are two great names. Wait, I did such a silly thing yesterday. I have to go to LA for a wedding. And I was like, what are people wearing in LA? Like, I don't know. Like, what should I pack?
Yeah.
And like on Pinterest, it like populates the genre of person you want to be, I guess. And one of them was baddie, was like one of the choices. Ooh. And I was like, okay, what if I click this and like go to LA as a baddie? And the outfits are insane. I'm 30 years old. These are like outfits for like very like 17-year-olds.
Oh, baddie is ageless.
I think Walter Baade might be ageless.
You go to LA and you be a baddie.
I need to dress like Walter Baade in LA. We'll see about dressing like...
No, I don't know for sure, but I imagine that involves a lot of like tweed
Oh my
jackets.
God, so hot. Something so hot and itchy, for sure.
Yeah, for sure. Whenever someone asks you, like, yeah, I'm in my Walter Baade. I'm in my baddie phase. My Walter Baade phase.
Exactly. That's what I mean.
Okay, so that part of the history was fun. You're not going to like this next part.
Oh, no.
I'm just telling you now. So the first neutron star was actually discovered in 1967, so about 30 years after they were hypothesized. And they were discovered by a Cambridge University grad student named Jocelyn Bell, who detected a really fast, regular pulse of radio waves coming from some specific point in the sky, in the Fox constellation. This is the part you're not going to like. And so there was a Nobel Prize in physics awarded for the discovery of the first neutron star.
I know where this is going to go.
But it did not go to Jocelyn. Yeah, it did not go to Jocelyn Bell. It instead went to her advisor.
Okay.
Whose name I don't even remember. But yeah, she discovered it. She did not get the Nobel Prize. She has not had a telescope named after her like Vera Rubin recently has. And so yeah, I'm waiting for Jocelyn Bell to get her flowers.
Yeah, that's a good name too.
Right? Yeah, we'll do a bio episode about Jocelyn Bell for sure. There are a few different types of neutron stars, or a couple different types of neutron stars, magnetars and pulsars. They both have very fun names that are kind of descriptive.
Magnetars, I don't know. I've heard of pulsars.
Yes, so there are more pulsars that have been discovered. The one that Jocelyn Bell found was a pulsar, which is probably why you've heard of it. Magnetars are, I think, equally interesting, but less common. Mm-hmm. So they're called a magnetar because they have extremely strong magnetic fields. Their magnetic fields are 1,000 times stronger than a typical neutron star, and 1,000 trillion times stronger than Earth's magnetic field.
1,000 trillion times. My mouth did drop.
Yeah, I saw it in real time. Your jaw dropped. Yeah, 1,000 trillion.
That number feels made up. Like, my little brain can't... I can barely get my head around a billion. Like, to imagine a trillion and 1,000 trillion.
Yeah, 1,000 trillions. It's almost 1 quadrillion times the strength of Earth's magnetic field. It's really strong. Just, like, unimaginably strong. And we aren't sure why their magnetic fields are so strong, which is like mind-blowing to me. We have ideas, like maybe it has something to do with the nature of the star that then became the magnetar. Like if it was a star with a really strong magnetic field. My hypothesis, and I am not a neutron star astronomer, I am barely a stellar astronomer, but my hypothesis is that it has something to do with the metallicity. Like if there are more metals, if there are more heavy elements in your star, maybe you are more likely to have a strong magnetic field. I don't know. I'm just
feels right.
Putting that out there as a maybe. Yeah. But people who are actually stellar astronomers who do study neutron stars do have other maybes. And one of these hypotheses is that maybe the interior of the neutron star, which we still don't totally understand, turns into a really cool superconducting fluid mixture of mostly neutrons, but also some quarks, which are fundamental particles that make up neutrons and protons, and something called a Bose-Einstein condensate, which is a special phase that you can get a material into if you put enough energy into it. So extremely energetic material in the interior of this neutron star might create a type of fluid mixture that is just extremely conductive.
Ooh, I'm trying to imagine what that looks like. I can't.
Yeah. And neither can scientists. But imagine really magnetic hot goop. Yep. I think
that's what I was thinking, and I gave it a silver color in my head.
Ooh, I like that. In my mind, it's just glittery like a disco ball.
I like that more.
Yeah.
Wait, do you know about the glitter mystery?
What, is the glitter shortage from TikTok?
Yes, exactly that. It's fun to call it a mystery.
But it's fake.
It is?
It's not. There is no glitter shortage.
What?
Yeah.
This is shocking me.
There is a
episode.
real helium shortage.
Helium shortage I knew about.
Glitter
I know.
Shortage.
I very guiltily got a helium tank for balloons. Now I feel bad.
Just chilling in your home.
Yeah, it's one of those little ones you get at a party supply store. If you need a balloon, I can get you one.
Cool. You got the hookup. Thank you, Corinne. Yeah, so I like to think of them like a disco ball. And maybe that's just because they give off very high energy light. So we mostly observe magnetars in X and gamma rays, which are the highest frequency part of the electromagnetic spectrum. Magnetars make up maybe 10% of neutron stars, and that's based on a combination of our observations, but also our theoretical models. And they only last for about 10,000 years before their magnetic field weakens. So one reason that their magnetic field is as strong as it is because they're rotating. And whenever you have a conductive material spinning, it's going to create a magnetic field. And so, like I said before, neutron stars slow down their rotation over time. So eventually it will pass this point where it's not rotating strong enough. The magnetic field will have weakened and we won't be able to observe it as a magnetar anymore. That is very different from the next type of neutron star, which is a pulsar. More people would have heard about pulsars than magnetars, although I think magnetars are cooler. I'm saying it here, folks. I think magnetars are cooler than pulsars.
Let's see how I imagine a pulsar, and then I'll tell you.
Oh, okay.
I'll tell you what my brain decided is a cooler look.
Yes. Well, what do you think a pulsar is or does?
Well, pulsar, I don't know if this is true, but the word pulsar makes me think pulse or some kind of throbbing action or...
Ew.
I know, it's truly gross. I don't know why I picked that word. I guess I mean pulsing action.
Yeah. Yes, although I will say that the name is kind of a misnomer.
Oh.
Because there are stars that pulse. We call them variable stars. They get bigger and smaller over time, like a heart beating. Mm-hmm. They do pulse. That is not what a pulsar does. So,
naming strikes again.
Again. Everywhere. It's going to come up every single episode.
Keeps you on your toes.
Mm-hmm. Most of the neutron stars that we've discovered are pulsars, but that does not mean that most neutron stars are pulsars. It's probably just that pulsars are easier to see than other types of neutron stars.
Okay.
So a pulsar is a rapidly spinning neutron star whose magnetic fields, because all of these neutron stars, all stars in general, they have magnetic fields. They might just not be as strong as a magnetar. And so you have a rapidly spinning neutron star with magnetic fields that focus beams of light to the poles of this star. Except it's not like the rotation poles. So the magnetic field lines aren't aligned with the rotation of the star. So instead of the beams of light coming out of the north and south poles, so to speak, they come out the side.
Oh.
So like if you picture the pulsar as a ball, it's rotating on one axis, and then the light beams are just coming like out the side of the ball.
Oh.
And if the orientation is right, then those beams will hit us as the pulsar spins, kind of like a lighthouse. And it's regular enough that we can count the amount of time between each beam of light hitting us, which we call a pulse, and we can measure things by that period, which is really cool.
Cool.
Yes. The periods of pulsars range from a millisecond, so 1,000th of a second, all the way up to 10 seconds. And these pulsars can last 100 million years before they cool down or slow down enough that the magnetic activity stops making those lights. And the like amount of time after, I guess, the moment in time when the pulsar stops pulsing, that's called the death line. Like, astronomers have decided to call it the death line.
Dark.
So dark, right? Yeah, and like that's just the amount of time that you have before the pulsar dies.
What happens after that? Do we know? Like, it just like lingers?
Yeah, then it's just a normal neutron star. And so neutron star is an umbrella term. You can have a neutron star that is a pulsar. You can have a neutron star that is a magnetar. You can have a neutron star that is both a pulsar and a magnetar. But then once they pass their death lines, they're just going to be a normal neutron star slowly radiating away all of their heat so that they go from 1 million degrees down to 0. And then they're just like a cold chunk of rock in space.
Aw.
Yeah. But that takes a long time.
Yeah. And maybe they like being a cold chunk of rock.
Yeah, maybe they do. I think they probably do, because it seems like a lot of responsibility to be a star.
Yep. There's a lot to do. You have to always be on.
Yes. There's no off switch.
There's no off switch. You can't be an introvert and a star.
Not out in space. Here on Earth you can.
Yeah.
Oh, hey, it's Moiya, and welcome to this episode's mid-break. Corinne is over there trying to persuade a butterfly to land on her finger, so now's a good time to shout out our patrons who support this podcast every single week. Thank you, as always, to our sun-like stars, Sharn Llewellyn, Finn, and Peyton. Let me know when y'all are throwing your next coronal mass ejection party, because I would love to join. We don't have any new patrons for this episode, but you can help us fix that by next week. If you want to join our Patreon for just about $1 an episode, you can do that at patreon.com/palebluepod. All of our patrons get access to research notes for every episode. You get to hear your name on this pod, and you can make it to our patron star chart, which you can find at our website, palebluepod.com. So again, you can support us on Patreon at patreon.com/palebluepod. And if you can't support us financially, that is totally fine. We and the universe still love you. But another great way to help our show grow is to share it with your friends. So pick your favorite episode and send it to your most curious or most space-afraid friend, and hopefully you will not only help Pale Blue Pod, but you will get a new friend for the universe. If you want to keep your brain healthy for a long time, studies show that you can do that with regular practice with analytical thinking. But the problem is that doing that type of analytical thinking isn't always fun. Enter Brilliant.org, the best way to learn math and science interactively online. Brilliant has thousands of lessons in math, science, and data analysis, and they add new ones every month. But Brilliant doesn't just teach you facts and formulas. They actually develop your intuition for these subjects through interactive gameplay. You're playing games and learning at the same time. Their science courses can help you get a deeper understanding of things that we talk about here, like planetary orbits. Become an expert in classical mechanics. Or you can use their lessons on quantum objects to learn more about the particle physics that we talk about every once in a while. Whatever you learn on Brilliant, you're going to have a fun time doing it, and it will strengthen your analytical thinking skills, which means your brain's going to look and feel great for a long time. So go to brilliant.org/palebluepod to get a 30-day free trial of Brilliant. And the first 200 people who do that will get 20% off their annual subscription. Again, that's brilliant.org/palebluepod for a 30-day free trial, or if you're an early enough adopter, you'll get 20% off your annual subscription. Next, I want to recommend another podcast for you that is part of the Multitude Collective, and it's called Games and Feelings. Games and Feelings is a very appropriately named advice podcast about, you guessed it, games and feelings. You can join Question Keeper Eric Silver and a revolving cast of guests as they answer your questions at the intersection of fun and humanity, because I don't know if you knew this, but you got to play games with other people. How do you convince people who have only played Monopoly to play the new board game you grabbed at the game store? Is an escape room a good third date? What makes a video game cozy, and do they have any recommendations for you? Games and Feelings is going to answer any and all questions as long as they're games related. And question askers get a fun advice nickname, like Rolling Bad in Carlsbad, or Bethesda Fan in Bethesda, Maryland. They're much better at coming up with cool names than I am. They also have Jasper Cartwright, who's an actor, D&D player, and host of 3 Black Halflings, as a permanent guest. Eric, Jasper, and various Multitude folks are recommending games, answering advice questions, and playing whatever quizzes Eric comes up with. What an interesting mind that person has. So if this sounds like fun, subscribe now wherever you get your podcasts to Games and Feelings. New episodes come out every Friday. So these pulses, these periods for the pulsars, they are so regular, we can literally set our clocks by them. By which I mean, if you have an array of pulsars and you have measured their periods really precisely, you can use that array, and we call it a pulsar timing array, to time things extremely precisely. They are more precise than like atomic clocks that we have here on Earth. They're amazing. So they take advantage of the regular periods of the very fast pulsars, specifically the millisecond pulsars, and then use them as clocks to study things in the universe that are hard to see. For example, we use pulsar timing rays to study gravitational waves. Gravitational waves are like ripples in the fabric of space-time. Technically, everything that has mass gives off gravitational waves, but we can only detect them from extremely massive sources. And we are using the pulsar timing arrays to determine when a gravitational wave has passed through an area. Because these gravitational waves, they will literally like stretch and contract space-time. Kind of like if you see something floating on a pool of water and ripples go through it, like it will move a little bit as the ripples pass. And so the same thing is going to happen to the pulsars, which means we can measure any like deviation to their period and know that something messed with the period of the pulsar. And it's important to have an array because gravitational waves will, as they're moving through, they'll like stretch things in one direction and shrink things in the like perpendicular direction. And so you need multiple pulsars in an array throughout space so that you can see if it shrinks in one direction, it better stretch in the other. And that's how you know it's a gravitational wave.
Cool.
The other big mystery that we use pulsar timing arrays to try and solve is the dark matter problem, especially on small scales, because all of the pulsars in our timing array are in the Milky Way galaxy, and we are trying to figure out how dark matter is distributed on small scales, like the scales of an individual galaxy. And so the way this works is that it's kind of like microlensing, which we talked about in our exoplanet episode, but the light from the pulsars has to pass through space. And if there is dark matter in the space, which we suspect there is everywhere, then it will also have to pass through dark matter. And using microlensing, so using the lensing effect of anything with mass, with a strong enough gravitational field, we can start to notice any irregularities in the timing of these light beams to find dark matter, which I think is very cool. Last week, I was at an amazing science communication conference at the Perimeter Institute for Theoretical Physics in Waterloo, Canada. And I saw like 3 or 4 talks on dark matter and quantum gravity and white holes, which are the theoretical like opposite of black holes. It was such a fun time, and I feel like I now understand better how we are searching for dark matter and how we're trying to figure out like the shape and distribution of dark matter in space.
Oh my gosh, that sounds so cool. I want to know about that.
It was also just like a cool, it was a science communication conference, not a science conference, although there were science talks. But most of the conference was just us science communicators talking about stuff that is really relevant to our field. And Corinne, I met the coolest people at this conference. I met the guy who makes minute physics. I met the guy who does the XKCD comics.
Oh, that's so fun.
Yeah, like I met some absolute like hard hitters in science communication, and it was really fun.
And they're like, and I met Moiya.
God, I hope so. We all now have a big group text going where we're talking mostly about all the geese that there were around the Perimeter Institute.
It is geese season. They
so
are out.
Many geese. They were out and they were aggressive.
They are not nice.
No.
And I think they don't know niceness doesn't exist in their world, but I wish it did.
You and I can go show them some kindness and be like goose ambassadors.
This is how you should be. See me?
Do as I do and as I say.
Dressed up as a goose, yeah. Teaching them how to be.
So we've talked about the different types of neutron stars, regular, magnetar, and pulsar. And now I want to talk about what happens when neutron stars collide. Because this does happen out there in the universe, and it gives us really interesting data to study. I was just talking about gravitational waves, so let's start with the 2017 LIGO detection of the first neutron-star merger. LIGO is the Laser Interferometer Gravitational Wave Observatory. It is 2 perpendicular hallways, long straight lines at a 90-degree angle, and they send a laser down each of these hallways, and the idea is that if a gravitational wave passes through the Earth, then it will also pass through LIGO, and you'll see that same stretching and contraction pattern that we would expect to see in the pulsar timing array. But it is something that we can build here on Earth and control, so like it's good to have both LIGO and the pulsar timing array. And in 2017, they announced their first detection of a neutron-star binary pair merging together. It was about 130 light years away from us, which means it took about 130 million years for the light to reach us from this system. So it is definitely out of the galaxy. Like, it is far away. It's not even in the local group of galaxies. It's further away than Andromeda. And so what happened with this collision was that the 2 stars were in a binary pair. So they were orbiting the center of mass of their system. And this is quite common because neutron stars form from very high mass main sequence stars, and those high mass stars are more likely to be born in pairs. So we expect that a lot of neutron stars also live in binary pairs. And over a lot of time, they will spiral in towards each other, radiating away gravitational energy. So we can think about gravitational energy just like we think about heat in a way. It's going to be radiated away, and the 2 stars will get closer and closer, and they get faster as they get closer together. And so they'll close the last 200 miles in milliseconds, and they'll collide, and it will be an extremely energetic event that will send out extreme gravitational waves that we can detect. And these events are important in space. It's good that they happen because they produce heavy elements like silver and uranium. And the 2017 one, they measured the amount of gold that was produced in the collision, not with LIGO. This was actually one of the first multi-messenger observations. When astronomers say multi-messenger, they mean we saw it in gravitational waves and we saw it in light, in electromagnetic waves. And so when they studied it with regular like light-seeing telescopes afterwards, they measured how much gold was produced, and that one collision produced more than a Jupiter's worth of gold.
Whoa, that's a lot.
Yeah. It's a lot. And so, massive stars don't make these heavy elements. They can get up to iron. So if you want the elements in your jewelry. Essentially, you have neutron star mergers to thank for that.
Yeah, I know. I'm looking at my wedding band right now. Thank you, Star.
Thank you, neutron star. And I saw this really cool study that says that neutron star mergers produce more gold than neutron star black hole mergers.
Oh.
Because yes, black holes and neutron stars can also collide, and they don't make as much gold, and we don't really know why.
Haha.
So that's neutron star mergers. I think that that's an important thing to cover when we're talking about neutron stars. But now I also just want to talk about, like, what are the coolest neutron stars out there?
That's all we want to know.
There are some awesome ones. Let's start with the first one ever discovered. It was a pulsar, and these pulsars are named after, like, their location in the sky. And so this pulsar is PSR B 1919 plus 21. That is its name.
Another perfect name.
And it was the first one discovered by Jocelyn Bell in 1967. When they discovered it, they weren't sure what it was. Like, people had thought of the idea of neutron stars, but there's no reason for people to see this regular pulse of radio waves and automatically assume it's a neutron star. Like, those two aren't linked. And so it took a lot of follow-up work to determine that it was a neutron star. But at first, when they were analyzing the data in a group, someone kind of, like, jokingly said that, oh, like, what if it's aliens? And so they named that first pulsar LGM-1. And LGM stands for Little Green Men. So it has two names, B 1919 plus 21, and also LGM-1.
LGM.
Little Green Man. LGM-1, I'll call it that, is about 1,000 light years away from us, and it pulses every 1.3 seconds. So it's a kind of intermediate period for a pulsar, but it is very important because it's the first one we found. It was also mentioned in Contact, in the book by Carl Sagan, and in the movie adaptation of it.
I know we just talked about Carl Sagan, and my head immediately forgot that it was a book. Nope, just the movie.
Yeah, someone on Twitter, after that episode came out, tweeted at us and said that they didn't realize Carl Sagan wrote the book Contact that the movie was based off of. Because, like,
why would you think that?
Why would you?
Why would there be some... Like, I think it's so rare for, like, a fictional movie, or, you know, just like a blockbuster-type movie to be based on a scientist's book.
Exactly. Yeah, and it's rare for a scientist to write a fiction book that becomes so popular. So, yeah. It's amazing that those two are linked.
I did Photoshop you holding a picture of him. I didn't Photoshop that. I'm sorry. That's a real picture.
I'm sorry. No, I was holding the picture.
I don't know if our listeners know, but I post a real picture of where we record each episode on the Instagram. It's Pale Blue Pod on Instagram.
She does.
You should check it out. Every picture is real. The continuity in our hair and makeup is extremely impressive.
All of those pictures are real, as are all of our recording locations.
Absolutely.
100%. We are in the botanical garden right now.
We are trustworthy and telling the truth.
So that was the first neutron star discovered. There is a top runner, a front runner for the most famous neutron star, and that has got to be the Crab pulsar. Crab. Everything's coming up. Crabs. That was a joke about how evolutionarily a lot of things end as crabs. That was not a joke about other types of crabs. So the crab pulsar.
Things end up as crabs?
Oh, there's like a joke that I see come up on Twitter often about how the crab is the most ideal form because crabs have evolved separately multiple times throughout Earth's history.
That spooks me. Crabs are... I did see a thing on Twitter that was showing this, like, very deep crab that we wouldn't normally see, but we're only seeing because the ocean's getting warmer. And it was like the scariest looking thing. Yes, like a spider crab or something. Bad energy. I didn't like it. I don't want that to keep happening. Like, we need to stop climate change. If I'm going to have to be looking at this, I won't do it.
Yeah, that's why we should stop climate change.
Because I can't stomach the weird stuff at the bottom of the ocean.
And we shouldn't have to. The Crab pulsar is a very bright pulsar in the Crab Nebula, about 6,500 light years away. It pulses 30 times a second.
Throbs. You mean throbs. The banned word.
The way you feel about megastructures, that's how I never want to hear that word on our podcast again.
I do think it's on the banned word list. The podcast now has a banned word list, and one of them is throb and throbbing in any form.
I didn't realize I had such a visceral reaction to that word until you said it, and now I know. So it pulses 30 times a second. And it is considered the most famous pulsar, or the most famous neutron star, because it is the remnant of a star that went supernova a long time ago. And that supernova was actually observed and recorded by Chinese astronomers in 1054 AD. Yeah.
Wow.
Yeah. And so, we have records of this old-ass supernova explosion, and then modern astronomers went to look where that supernova happened, and they found this pulsar. And now there is, really cool evidence that links pulsars and neutron stars in general to supernova explosions because of archaeological evidence. And I think that this is just such a beautiful example of the humanities and the social sciences and the physical sciences working together, and it makes me happy.
Well, I don't really think of archaeology, or I think I'm learning through this pod how recent so many of these discoveries are, and it's so fun to think that there are way older ones that we can use for modern day research.
Yes, because the thing about a supernova is that it is so bright that even from 6,500 light years away, so it's still in the Milky Way galaxy, but very far away, it looks like a new, very bright star has just appeared in the sky overnight. Mm-hmm. And so ancient people, it was 1,000 years ago, so it's not that ancient. But for a long time, humans were looking at the sky and recording what they saw in it. And whenever something went missing or whenever something new appeared, it was noteworthy. So we can now comb through the records that remain and do actual modern day science with it. And that is just the most clear-cut example of what I am doing in my career as an astronomer and folklorist. It makes me really happy to see this. Aww. I'm not gonna cry again. If it sounds like I'm crying in my voice, that's just because I'm sick. It's not because I'm emotional. The next magnetar, the next neutron star that we're going to talk about is a magnetar, because I think it's important to have representation from different types of neutron stars. And so this magnetar, I guess maybe it's the most infamous neutron star. If we have a list of banned words, I think infamous is on our list of words we want to use.
Infamous, I don't know if I've said this on the pod. Back when AIM was coming out, I knew someone who had infamous in their screen name, and I thought it meant not famous.
Yeah.
And I was like, that's so funny.
Well, kind of. So this magnetar, which I'm officially deciding is the most infamous neutron star, is called SGR 1806-20. And SGR is an initialism. It stands for soft gamma ray repeater, which is something that they sometimes call a magnetar because it gives off soft gamma rays. So there are hard gamma rays and there are soft gamma rays, and it's just a matter of their frequency. Soft gamma ray would have a longer wavelength or a lower frequency than a hard gamma ray. So this magnetar is about 50,000 light years away. So it could be in the Milky Way, but it could also be out. I'm pretty sure it's in the Milky Way. In 2004, it had a magnetic flare, or at least we witnessed a magnetic flare on this magnetar, which is something they do all the time. They're magnetars. They flare up anytime there's any type of interruption in their crust. So it's like a soup of superconducting neutrons underneath, but there's also this very thin crust of like electrons on the outside of a neutron star. And anytime there's an interruption in that crust, it's gonna flare up with magnetic activity. So that happened in 2004, and in just a few seconds, that magnetar released more energy than our sun does in 150,000 years.
Whoa.
Whoa is right. It released so much energy that even from 50,000 light years away, that magnetar's pulse affected our satellites and ionized a bit of our atmosphere.
Whoa.
Yeah. And it would have been really, really bad if that magnetar was within 10 light years of us. It would have, like, stripped away our atmosphere, or at least, like, ionized so much of our atmosphere that, like, our atmosphere had all of a sudden different composition. It would have been extremely terrible if it happened within 10 light years. But luckily for us, the nearest magnetar is more than 8,000 light years away. It's called XTE J1810-197. That is the closest magnetar we have found. So that's well outside the bounds. But the fact remains that these magnetars are so powerful when they flare up that even from across the galaxy, we can feel their effects, even if it's not dangerous. Wild. Wild to me.
That is wild. I like feeling like we're all connected, but I hate to think that it's threatening to my way of life.
But that's the thing. There is not a magnetar close enough to hurt us. And if you know, like, people can be like, oh, but what if there is and we just haven't found it? But no, because they are bright enough that if it were going to flare and it was that close, we would have detected it. We would
see it.
Yeah, at this point, we've scanned the whole sky, like the whole sphere, and the only things we can't find are things that are really dim and really far away. So we're safe from magnetars.
Okay. Phew. It does sound like a villain name.
A magnetar? Yeah, it kind of does. Now I really want to write a story about, like, a villainous magnetar, 1806-20, that, like, destroys...
Yeah.
tries to destroy the Earth from across the galaxy and utterly fails.
It's like a Wicked story where there's, like, a magnetar and a pulsar of, like, a green... like, Good Witch and the Bad Witch.
Little green man.
Little green man? Magnetars might just be misunderstood.
Yeah. Yeah, probably. I would befriend a magnetar if I could. So those are the three coolest neutron stars that I wanted to talk about. But I do have to give an honorable mention, as an exoplanet girly, to PSR B1257 plus 12. That is the pulsar that hosted the first exoplanets we ever discovered back in 1992. And so it has to be on the list, although the pulsar itself is not super interesting. It's just the fact that it has planets around it, which means most likely that it was a massive star that had its own planetary system, and then the star went supernova, and the neutron star left behind maintained these planets in its orbit, which is impressive.
That is impressive.
To, like, survive a supernova explosion, yeah.
Yeah.
Though that's everything I wanted to tell you about neutron stars, Corinne. How are you feeling now?
I like that stars can kind of still be doing stuff on their way out.
Yeah.
I think that's fun. How far away is our sun from being a neutron star?
Great question. Our sun will not become a neutron star. Our sun is just under the mass cutoff for a supernova explosion, which means our sun, in about 4.5 billion years, is going to puff up into a red giant, so it'll get, like, really, really big, and a little bit more hot. When it does that, it's going to be, we think, as big as Mars's orbit today.
Okay.
And then, because it's so hot, it's going to take off its clothes. This is how I like to explain it. It's going to, like, take off its clothes, and it's going to shed a bunch of gas and other material in the outer layers. And what's left behind is going to be a little white dwarf, which also won't be fusing hydrogen into helium in its core. And so it, very similar to a neutron star, is just going to radiate away whatever heat and energy it has left for the next, like, few billion or trillion years.
Okay, well, that's great news to me. As if I would survive that. As if it's in my lifetime and as if I would survive it.
Right, as if, Corinne, you're going to live to be 5 billion years old.
I might.
I believe it. I hope you do, but without, like, all the bad parts of that.
I know. Tuck Everlasting really soured me on living forever.
Yeah. I mean, that's one of the things that puts me off of a lot of vampire stories. Not completely. Yeah. I'm still gonna consume a vampire story because they're hot, but the whole living forever thing among humans sounds really difficult for me.
Yes. Yeah, it has to be selected. Like, I need a desert island kind of group. Like, I've handpicked who we are.
Yes. Your 5 billion club.
Yeah, it's us and all our listeners and a dog.
Just one. We can share it around.
Yeah.
Oh, okay, great. Well, if you have no other questions or concerns about neutron stars, then I would really like to explore the rest of this garden.
Oh, we have to. I think they just redid part of it, and I'm dying to see.
Okay, then let's go see the new parts. And listeners, whatever plants are surrounding you, whatever stage of life you're in, remember, you are space. Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.